is formed, we are not going to see these cells repair. All right, so what you got is what you got. Okay, now basically the way that they're going to connect, they're going to connect like this, one cell, and just have a little tiny bit of what looks like an overlap. The reason for that, we're going to see them at this overlap be connected by what we term the intercalated discs. What that's going to allow for in this, what they call interdigitating folds, because it literally looks like digits, okay, fingers doing this number, having a little bit of an overlap in this fold area. In that area, what we're going to see, we're going to have some mechanical junctions. Do you guys remember when you were talking about in part 1 cell-to-cell connections, how you had tight junctions, gap junctions, desmosomes, that sort of thing? Okay, in the heart muscle, because of the structure that's been formed, this little bit of interdigitating that takes place, it increases my surface area. We're going to see that it has the ability to lock together. We're going to have our desmosomes. Do you guys remember how you'd have like part of one in one cell, part of one in another cell, and it helped hold them together? And then we're going to definitely have some gap junctions, because gap junctions are, just like the name implies, they're a gap. And they're going to allow for the movement of materials. And we're going to have in this little piece that folds over something that is termed fascia adherens. Anytime you hear the term fascia, hopefully they talked about this in part 1. Fascia means a sheet of connective tissue. So these folds have the fascia, and it's called adherence, to adhere, to keep them to stay together. Think of like Velcro, okay? That fascia is to hold them together, okay? This is our actin and our myosin. Do you remember actin and myosin? And skeletal muscles, it created the sliding filament model. On smooth muscle, it does like a triangle and does this number to contract smooth muscle. Okay? In heart muscle, it's going to allow it to go for contraction, okay, based on the structure. So, we're dependent on having this interdigitating, okay, with, I mean, really good gap junctions, because when that electrical signal starts and travels, which we're going to look at, as it travels, even though the heart looks like it beats in one action, it's the ability of every single cell with those gap junctions passing those electrical currents, one cell to one cell, and them working like they should. Each individual cell has to do its job. This structure that the heart has is allowing for those ions, sodiums, potassiums, calciums, to flow from one cell to the next, affecting their polarization. Do you remember anything about polarization? For something to be polarized, depolarized, hyperpolarized? Michelle?
Is that with the exchange whenever the sodium enters the cell, the intracellular fluid, and then potassium is released? So the depolarization is when sodium goes in.
Sodium goes in, repolarization, sodium's pushed back out, potassium's equalized. So if you remember, you should have had something like this, where this, of course, positive, this is negative, this is positive, this is negative. Everybody recognize that? And like when we talked about it with muscles, okay, the muscles are at rest. Does everybody remember a resting potential? And muscles would be at rest, and then they would get the information from a nerve to begin to contract, and you would see it go up and then come back down and go back to relax, okay? Same principle, okay? We're going to see, now think about this for a second. How many times did they say the heart was beating? How much? 100,000 a day, and they gave us something in the millions for something, and I was trying to do some math in my head about, okay, well, if average lifespan is 75 years, and I want to multiply it times that million number, I couldn't do that math, okay? Would you believe the heart cells get to rest in between each contraction? Just doesn't seem like it's present, all right? But it is. So, once again, we always have to start in the negatives, okay? Because the electricity in our bodies, it can't be like what we think about over here with a plug-in at 120 volts, but that's still operating off ions, okay? Our body is operating on ions. It's just at a lower level, okay? Now, if we start at this, we're going to see that heart do this number like that. Does everybody remember that? Where we depolarize, repolarize, okay? It becomes important to make sure that these ions, see how we've got like this interdigitating that takes place, and they're showing these gap junctions, okay? That we're going to have the movement of those materials through those heart cells, all right? Then we're going to pass those ions and create that conductivity. So, in these cells, all right, because when you look at one cell, we've got the one nucleus, we've got our intercalated discs, and in the heart, the mitochondria are very numerous, and they're huge in the heart cells, okay? And this is how it looked under the scope. Not sure if everybody remembers that, okay? But one thing about heart muscle has to work aerobically, meaning every bit of work that the heart does, we are dependent on those mitochondria using oxygen and giving us those 36 to 38 ATPs. It cannot survive anaerobic fermentation. Now, why is that clinically significant. Note that it can use fatty acids, glucose, ketones, lactate, amino acids, just about any food source it can get. Clinical significance of this. We are looking at our cardiovascular system. My heart, my vessels. Now, the heart is a pump. It's working 24/7. It's beating a lot, okay? And the goal, move this fluid around the body. Something happens. I end up with a huge gash somewhere. Something begins to start making the blood flow. And then, I don't know, maybe it could be a situation where somebody has, I don't know, passed out or something. And always they begin watching the clock.
See how long, like, they're down without the proper oxygen.
Like if that heart stops, or if something else begins to affect. What's the time limit that they're looking at? How many minutes? 5. Now, you cut an artery. If you don't staunch that flow, chances are within 2 minutes you're dead. We talk about cutting an artery, you got to staunch that flow quick. And when I say quick, I mean quick. Okay? Why 5 minutes?
Because it causes major damage to the brain.
Do you know why?
Because of the lack of oxygen.
We've got the lack of oxygen. Do what, Emily?
Tissues die.
Tissues are going to die if they're not getting the blood flow.
Is there enough residual oxygen in the tissue to survive for the 5 minutes?
Not enough. It's not in the tissues.
Blood.
We're losing blood, but do what else?
Yeah, is this enough still in the blood circulating?
Which side? Artery or veins?
It's venous.
Venous. You're going to find the vessels of the body, the veins, are termed capacitance. They will have up to 5 minutes worth of oxygen. And the last thing you want to do is deprive these tissues of the body oxygen. So the heart muscle, when oxygen is no longer available, oxygen gets cut. Something happens, okay? Heart muscle cannot withstand that. It will die, and no matter what happens on how death comes about, death is always the heart stops beating. People can have pacemakers, be dead, but they're still alive. Literally. Yeah, it's kind of freaky when you learn about pacemakers. But this muscle right here, it has to work aerobically. Now, that muscle, which is extremely specialized, okay? But once again, the actual contraction of it is based upon the heart setting its own beat. The way that the heart is going to set its own beat, this conduction system